So here is the introduction from the lab guide. And some students asked me about the water analogy. In trying to understand electricity, having a model or analogy, because models are basically analogies, makes it so it's easier to think about what's going on. So here we have two variations of a circuit, one being an electric circuit. It has a power supply and wires and a light bulb. The other one is a water circuit. It has a pump, has a holding tank up on top, a holding tank on bottom, and then it has a pipe and a turbine. Now the analogy is this. What does a pump do to water? In this circuit, what is the pump doing to the water? It's, in terms of the tanks, it's moving water from the low tank to the high tank. That's giving it gravitational potential energy. So the gravitational potential energy per molecule of water is higher in the top tank than it is in the lower tank. Right? On the other circuit, we have the power supply that's doing the same thing. It's raising the electric potential energy instead of gravitational potential energy per charge. So on the top side of the power supply, this right here is analogous to this right here, where the pump has raised the potential energy of each molecule or of each electron. Then we have the pipes that the water flows through. Actually, I should have changed colors. We have the pipes that the water flows through. All those do is make a pathway. And of course, in the electric circuit, what's making the pathway? Wire. The wire. So the wire is doing the same function as the water pipes. And just like with water pipes, if the wire has a bigger diameter, it's going to have less resistance to water going through, or to charge going through. And if it's a longer, it's going to have more resistance. And then we have the turbine. The turbine is converting the potential energy into some kind of other energy. Over here, the light bulb is converting the potential energy into some other kind of energy. In the case of the light bulb, it's converting the potential energy the charge had into light energy, 5%, and thermal energy, 95%. In the water analogy, you're turning that turbine, assumedly charging a battery with it or something. Now, I talked about the analogy for voltage, the elevation, right? The higher the elevation, the higher your gravitational potential energy per mass or per molecule, or the higher the voltage, the higher your electric potential energy per electron. The current is just the flow rate, how fast the charge is going through a wire, or how fast the water, how many molecules per second, is going through the pipe. So that's what the analogy is there, to just help you think about, what does current really mean? What does voltage really mean? Any questions about the analogy there? No? Okay. All right. And then let's just go straight to, there's Ohm's law, the series and parallel parts. I will talk about the meters, but after I talk about these. Here I've drawn series and parallel combinations for resistors as well as physical batteries. Notice the symbol for the resistor. It's important that you have sharp lines, sharp edges on both sides. Because if, for instance, you draw something like this, that means an inductor. It's a different thing. So it's important that you have, so I'll put L for inductor. It's important that you have sharp edges on that to indicate that it's a resistor. And of course you can see vertical, horizontal. Who cares what direction the resistor is drawn? That's a resistor. In the top circuit, we have the resistors arranged in series. If I have current that goes in here, it has to keep going. And all of these are going to have the same current going through them. That's what defines them being in series. So series has the same current through everything. There's no alternative pathway. The parallel, on the other hand, all of the tops are connected together. And all of the bottoms are connected together. So that means that the voltage difference is the same for each item that is in parallel. So parallel circuits have the same voltage across everything. Series circuits have the same current through everything. Now, just a little tricky question. Okay, that's enough. Are these resistors in series or parallel? Okay, they're in series. I drew them like they're parallel for why? Well, just to make sure we understand, you don't just look at the orientations of the resistors to determine if they're series and parallel. You look at the connections. And in this case, I would have had to have my current go through each one the same current, no way for it to branch off. What about something like this? This is what we call a bridge. It's about the sloppiest bridge you'll ever see. The answer is, if I have current coming here, it splits like this and this. So the current doesn't have to go from one to another. It means it can't be series. Now the tops of these are connected together, but the bottom, those are not connected to the same thing. So they can't be parallel. So this is neither series nor parallel. So not every connection is series or parallel. Oftentimes we just fall into the trap. We learn series, we learn parallel, and we think everything must be one or the other. But they don't have to be. Now with the resistors, your hypothesis deals with the resistors. So with the series and parallel. So remind me to come back to that before we start the experiment, because it's important that I go over that part. I'm going to do some calculations with that. But before I do those calculations, I want to go to how we make a circuit. The first thing you have to do in the lab is not experiment, it's making sure you know how to make a circuit. So you're given, it shows in the lab a picture that has this and this. What is this thing on the left? That's a battery or a cell or a power supply, whatever. In truth, it would be a cell. But it can be whatever. People aren't very accurate. What about the thing on the right side? Resistor. Now, if I'm going to make a circuit, what is the fundamental thing that defines a circuit? Looking at you, Bridget. What's the fundamental thing that defines a circuit?
Oh, okay. What goes around comes back around.
Yeah, it has to go around and come back on itself. So how can I make this so it goes around and comes back on itself? Yeah, all I have to do is connect them, right? Now I have a loop. Now I can have my current come out of the positive, go through the resistor, and go into the negative. So now I have a circuit. But we're going to measure the voltage and resistance for this resistor, or not voltage and resistance, the voltage and current for this resistor. We talked about voltage measurement. What words did I use for how we measure voltage? In blank. There's only two options here. It has to be, no, I heard somebody say it has to be measured in parallel. That is, you're measuring the difference in the potential energy per charge from one side to the other. So if I'm going to measure my voltage, I need to connect across and put my voltmeter in parallel like that. Now, redrawing my circuit won't take but a moment. We also need to measure the current. How did we measure the current? That's right. In series. Because we need to measure how much is going through. So to measure the current, I need to break my circuit and then put my current meter in series with the item I'm measuring the current through. So here I've shown how we measure the voltage and how we measure the current. You need to draw a circuit for how you would measure both the voltage across the resistor and the current through the resistor. Now, as I talked it over with Bridget, so she can verify, there is not a perfect circuit for measuring both the voltage and the current. But there are two that are approximately correct. Now, I say approximately correct because a voltmeter, this here is a voltmeter, has very high resistance. So you take your voltmeter and you put it in what kind of arrangement with the resistor? I want to measure the voltage across resistor. How do I connect my voltmeter with that resistor? In parallel. So I'm going to take this voltmeter and put it in parallel with the resistor. I have the same voltage across both of those, right? Because parallel circuits have the same voltage. And each one will have some current going through. How can I relate the voltage to the current? Current equals Ohm's law says V over R. So both the resistor and the ohm meter have the same voltage, but they have different resistances. The ohm meter has a very high resistance. If the ohm meter has a very high resistance, how much current is going through the ohm meter? A very small amount. So the ohm meter won't make much difference. So it's not a big problem in messing you up. But it does siphon off just a little bit of current. Now if we go the other way and we look at an ammeter, as we call it, ammeter because we're measuring amperes. The ammeter's in series. An ammeter has very low resistance. So now if I have current going through the resistor, there's a voltage drop across the resistor that according to Ohm's law is V equals IR. If it's the same, well, what is the same for series elements? Series, they have the same current. So if they have the same current and the ammeter has a very low resistance, what does that tell you about the voltage drop across it? It's very low. So the voltage drop caused by the ammeter is very low. So once again, it doesn't affect the circuit very much. Now it's because the ammeter has that low resistance that we have to be careful with ammeters. If you do something like take your current probe and connect it to the power socket here, you essentially are putting no resistance between a high voltage. We call that no resistance is short. Using that relationship, if I have a high voltage, let's look at the Ohm's law version on the right. If the voltage is high and the resistance is low, what is the current? Super high. And so you can easily go past the 1 amp of our ammeters or the 15 amps that the building supplies and cause faults. So you have to be careful with ohm meters or you will destroy them or other things. For that reason, when you're doing your experiment, you need to have Erika, or me come by and check your circuit before you turn on the power to make sure that you don't have something connected wrong and cause a real problem. Okay, now that I've talked about the meters, I will talk about the series and parallel. So now you don't have to worry about reminding me, I remember. If I take a power supply and I connect it to three resistors, R1, R2, and R3. First of all, are these series or parallel? And given that these are parallel, what's the same for all of them? Same, not save, same voltage. So I have some EMF here, and in terms of current, how is current going to flow? I have current that comes out of my battery, and what's it going to do when it gets here? Some of it will go down, some will keep going. What about when it gets here? And when it gets here, it all goes down because there's no other path. And then it will come and it will join up together. And come back. And so all of the current that left here is going to be coming back here. We didn't use up the current, it just cycled. Now, an equivalent circuit has the same power supply, but just one resistor. Now, if it's equivalent, the power supply has to have the same EMF, and what would the other thing be? Power supply can't tell the difference, so what two things have to be the same? The current and voltage. If the voltage was different, the power supply would say, ho, you connect me to something else. So the current has to be the same for both cases. I'm going to call the currents up here I1, I2, I3. Here I have I, and here I had the same I. Now if I go through and analyze these circuits, I can say for each one of these resistors that I have current 1 is equal to, according to Ohm's law, the voltage, the EMF, over R1. Current 2 is equal to the EMF over R2, and current 3 is equal to the EMF over R3. Right? Now if I come to this circuit, I just have the current is equal to the EMF over the equivalent resistance. How can I relate these two? I have a current I comes out and it's split off into I1, I2, and I3. Because the charge can't be created or destroyed, we don't use up the current. We have to have I equals I1 plus I2 plus I3. Well, if I look at these, notice each one has the EMF on top. But I was equal to EMF over R equivalent. So if I take the left side of this and set it equal to the right side, I have Now you might ask, wait a minute, there was an EMF in every single term. Why is there no EMF in my answer? Yeah, it was in every single term, so I canceled it out. So that's how resistors add when you put them in parallel. If you take this number, just think about it. Let's say I had two 10 ohm resistors. Just two, so I'm not going to look at the last one. I'd have 1 over 10 plus 1 over 10, which is clearly 2 over 10, or 1 over 5, would be equal to 1 over R equivalent. What would R equivalent be then? Be 5 ohms. So if I have two 10 ohm resistors in parallel, it's equivalent to 5 ohms. It went down, right? In fact, it's always going to be true. Anytime you put resistors in parallel, the equivalent resistance will always be lower than the lowest one. Now let's go to putting them in series. So if we put them in series, now what's the same for all of the resistors? The current has to be the same for all of them. So since the current's the same for all of them, I'm going to calculate the voltages. The voltage 1 is equal to IR1, voltage 2 is equal to IR2, and voltage 3 is equal to IR3. In my equivalent circuit, it's still the same equivalent circuit. And what is my total EMF equal to? I times, for the equivalent circuit, did you see that? The warning that my battery's about to die? Actually, I got 15% left. In this circuit here, it has to have the same current, and so I'm going to have the EMF is equal to the current times the R equivalent. Just like we did before, well, not just like, because I have all these resistors in series, what did I do when I was talking about the batteries that I put in series? Remember when we talked about Cassie's question? What did I do with the voltages when I put the batteries in series? I added them up. The total voltage was the sum of the ones that I put together. So in this case, I should have the EMF is equal to V1 plus V2 plus V3. So if I set these equal to each other, and of course the currents equal to each other, I'm going to have IR1 plus IR2 plus IR3 equals IR equivalent. Once again, cancel out the I's, and you have R equivalent is equal to R1 plus R2 plus R3. So resistors in series just add algebraically. Now if I have two 10 ohm resistors and I put them together in series, how big is that going to be? 20 ohms. Resistors in series always add to something bigger. Resistors in parallel, always something small. You had a question?
I was just curious, if you have multiple resistors and they just equal the resistor equivalent, what's the point of adding multiple resistors?
The point of putting the multiple resistors is usually because you're doing something like, I'm trying to get 70% of the voltage here and 30% of the voltage here, or something like that. Or maybe I just couldn't get the right resistors. All right, now let's look at the actual, right, here's the rules on adding and all that. The color codes and then the actual experiment. Resistors are typically identified by color codes. We have a couple of boxes with resistors in them, and you're going to go choose one for your required experiment, more for your hypothesis test. And those resistors have a color code. And usual average standard resistors, you have 4 colors. The first 2 colors tell you the numerical value. The third color tells you the magnitude. And then the last color tells you how carefully it was made, how much the uncertainty is in the resistor. So the way we put this together is we have a color code set: black, brown, red, orange, yellow, green, blue, violet, gray, white. We had a mnemonic that was inappropriate that I learned when I was in college. So those colors stand for numbers. Black is 0, brown is 1, red is 2, and so on. People have pointed out to me since then that from here to here is the colors of the rainbow. Yeah, I didn't even notice that when I was in college. I just, learned my own thing. Well, I didn't come up with it. But these they just tell you a number. So if you look at this here, you have blue. Look over here for blue, and you say, oh, that's a 6. And then you have red. You look over here for red, that's a 2. Then we have yellow. Look over here for yellow, and that's a 4. And then the last one goes over here. And so this here is supposed to be silver, and silver is plus or minus 10%. Now how you read this is, take the first 2 numbers, 62 times 10 raised to, and that's 4. So that's how you read it. The first 2 numbers times 10 raised to the last one, and then the third one, then final one's the uncertainty. With our resistors for today, you're going to choose a resistor, make sure you write down the color code, and calculate what its nominal resistance. Nominal is a name. That's how they named it. This here was named a 620 kilo ohm resistor. So you're going to determine what its resistance is, its nominal value, and its uncertainty. We're going to compare that to what you get from actual measurements. Make sure that the resistors you choose have the third band brown. If it has the third band brown, what does that mean? You're going to be multiplying numbers by what? By 10. So we have 2 digits multiplied by 10, which means they're all going to be in the hundreds. So they all should be in the hundreds of ohms, 100, 200, 150, whatever. The reason we're doing that is because we want to make sure the current is less than, what's our maximum here? I is V over R. The maximum voltage we're going to use is 10 volts. And the minimum resistance we would have would be 100 ohms. That would be 0.1 amps. That's why we're setting that limit. If you choose one that has black for the third line, then you're going to draw too much current. If you choose one that's red, your current's going to be small. If you choose one that is orange or beyond, your current's going to be really small. So that's why we're choosing to have the third band black. Okay, now we're really truly getting to the actual experiment. Your hypothesis. It must relate to how resistors add in series or parallel. So you need something that's going to deal with how resistors add in series or parallel, and then your experiment needs to be something you can make with our single power supply and multiple resistors. So your hypothesis should be, something like, I notice we can't say in my calculator there are 2 batteries because those aren't resistors, right? But, I notice that something like light bulbs. Light bulbs are resistors. You know, there are lots of things that are resistors you can think about. But your observation, you know, something that has multiple things put either in series or parallel, and how it works, and then an explanation of why it does that based on how resistors add in series or parallel, and then a prediction that you can make from that that's different than, of course, your observation that you can test by measuring the current, voltage, and subsequently resistance of resistors in series or parallel compared to a single resistor. So that's what we have for our prescription of the hypothesis and the test there. I've already talked about this first part, making the circuit. You're going to actually make the circuit and test it. And the testing is, as I was telling Cassie, 5 minutes. It really is that fast. So once you've made your circuit and you've had Erica or me check it to make sure that everything's good, you open up the Ohm's law in Capstone, and your display should look like this. This here says signal generator. Make sure that it says DC. I mean, it should be. You can't save over it, and I've saved it to say DC. And right now it says 0 volts. It's on auto. That means that when you click the button here to preview, it'll turn the voltage on. So don't click preview until after we've checked it. You're going to want to start with this at 0 volts. You connect your circuit using the outputs. I don't have a picture of it here, so I'm grabbing one. Using the outputs right there. Those are our outputs that we're using in today's experiment, the red and the black. The red one is going to be the one that has your voltage going up to 10 volts, no higher than 10 volts, and the black one is the other side, the ground. So those are your power for your circuit. When you're ready, you say preview. It reads the voltage here. It reads the current here. Write those down. Then hit this button. Boom, 1 volt. The voltage number will change. The current number will change. Write them down. Hit this here. Actually, wait, no, I forgot. You need to write them down, but first you need to hit click keep sample. So at 0 volts, you hit keep sample. And it will actually, there, now you can see. It'll put them right here and here. Write them down in your lab guide, though. Don't just say, oh, they're there. Write them down. Then you go up to 1, hit keep sample. It'll put them here. Write them down. Go up to 2, hit keep sample. Write them down. When you get up to 10, stop. Make sense? Pretty straightforward, right? This will actually make the graph for you. And remember to print the graph. Select this here, and this should be on snapshot workbook page display. Then I'll take the picture, and then I just took the picture of the graph. After you're done, so after you've done your hypothesis test as well as this, then print out the ones. Remember, you can turn on the journal here to see what you've saved. That's it. There are some questions to answer, but those are just questions to answer. Any questions? Okay, we should have even groups of 2. Get started.